Picture this. You are strapped into a seat at 35,000 feet, dark outside, both engines humming in perfect sync. The flight is routine, the kind you have taken 100 times before. Then the cabin goes quiet, not in sound, but in meaning. A number vanishes from the flight deck display, and the crew knows before any instrument confirms it that the aircraft has changed forever. The aircraft breaks apart. 9 miles of uncontrolled descent through air cold enough to freeze flesh in seconds. A field of debris scattered across a landscape that will become a crime scene for investigators. And somewhere in that wreckage, a small orange box, the size of a shoebox, has just survived forces that turned aluminum into confetti. It will hold the only complete testimony of the final moments of that flight. The black box, you imagine, the indestructible device that records everything from every angle, does not exist. But the real device, the one that actually exists, has a survival story far stranger than the myth. It is not black, it is not indestructible, and the engineering that allows it to survive what no human body can endure is a masterpiece of defensive design, built from the lessons of past failures. By the time this investigation is over, you will never see that small rectangular unit near the tail the same way again. You will understand what it takes for a memory chip to survive the impossible. The real story begins inside a cold, dark hole in the ocean floor, where a tiny orange box sits broadcasting its location for 30 days straight, waiting for someone to come find it. That is where the engineering of survival truly meets its final test. You may think you know what a black box is. Most passengers think it is a device that records everything from cockpit conversations to instrument readings with perfect fidelity. The assumption is natural. Hollywood has trained us to see the black box as an all-seeing, all-knowing witness inside the aircraft. A silent guardian that stores every word and every number. But the truth is far more specific and far more interesting. The flight recorder does not record everything. It does not record video. It does not store continuous audio in the way you imagine. The cockpit voice recorder stores the last 2 hours of audio on a loop, overwriting itself every 120 minutes. The flight data recorder captures hundreds of parameters, but only for the most recent 25 hours. The device is not designed to preserve every detail of the flight. It is designed to preserve the last moments before something goes wrong, the critical window that investigators need to understand what happened. This distinction matters because it changes the engineering challenge. The recorder does not need to survive a routine flight. It needs to survive the one flight where everything fails. And surviving that flight means enduring conditions that no consumer electronic device on Earth could withstand for even a fraction of a second. Think about the fragility of the smartphone in your pocket. A drop from waist height onto concrete can shatter its screen and destroy its internal components permanently. Now imagine that same smartphone being subjected to an impact that generates a deceleration of 3,400 times the force of gravity. That is the survival requirement for the crash survivable memory unit inside every modern flight recorder. 3,400 Gs. The human body would be reduced to its constituent elements at a fraction of that force. The fragile silicon chips inside the recorder must remain intact and readable. Here is where the engineering becomes brilliant. The memory module is not simply a reinforced box. It is a layered system of defense that absorbs and dissipates energy through multiple independent mechanisms. The outer case is constructed from titanium alloy or stainless steel, up to 1 inch thick in critical areas. That is the first line of defense against penetration. a hard shell that resists tearing and puncture. But brute strength alone would fail. The real secret lies inside the case, where the memory boards are mounted on a stack of shock-absorbing plates separated by layers of thermal insulation. That decoupling, the deliberate use of compliant layers between rigid barriers, is the kind of engineering insight that turns a routine passenger into an informed observer. If you want to keep peering behind the panels and into the real logic of aviation design, subscribe so the next revelation lands in your feed. And before you continue, drop a number in the comments. How many G-forces do you think a human spine could survive if we engineered a similar multi-layer system? This is the core insight that most people never consider. The recorder does not absorb the entire impact through a single rigid structure. It distributes the force across multiple plates that bend and compress, extending the deceleration time and reducing the peak G-load on the memory chips. The same principle governs the design of bulletproof vests and spacecraft landing systems. Spreading the force over time and distance is more effective than trying to stop it all at once. And the thermal challenge is even more demanding. The recorder is required to survive a fire that reaches 1,100 degrees Celsius for a full 60 minutes. That is hotter than molten lava. Hot enough to melt aluminum. Hot enough to vaporize the solder joints that connect the memory chips to their circuit boards. The titanium case alone cannot provide enough thermal protection. Engineers solved this problem by packing the interior with a specialized ceramic-based thermal insulation that is identical in function to the heat shields used on spacecraft re-entering the Earth atmosphere. The memory module is effectively contained inside a miniature re-entry vehicle. It is designed to stay cool while the world around it burns at temperatures that would destroy almost any known material. But the most astonishing requirement involves penetration resistance. The recorder must survive a direct strike from a 227-kilogram weight, dropped from a height of 3 meters. That is roughly the weight of a grand piano falling from the height of a second-story window, concentrated onto a single point. The case must prevent that force from reaching the memory chips inside. And then there is the deepest requirement of all. The recorder is designed to withstand immersion in the ocean at pressures equivalent to 6,000 meters of depth, over 20,000 feet underwater, for 30 consecutive days. At that depth, the water pressure exceeds 600 atmospheres. The weight of the entire water column above presses down on the recorder with forces that would crush a submarine hull, not designed for such extremes. The locator beacon must continue transmitting its signal through that crushing pressure for the entire 30-day period, broadcasting the recorder location to search teams that may be scanning thousands of square miles of ocean surface. This is where the term black box becomes meaningful, but not for the reason you might think. The devices are not black at all. They are painted bright fluorescent orange to maximize visibility against the dark ocean floor or a green forest floor. The term black box emerged from early aviation engineering slang for any sealed electronic device whose internal workings were considered mysterious or classified. The name stuck even as the color changed to orange for practical survival reasons. Now consider the parallel timeline that shaped this design. The earliest flight recorders were nothing like the titanium-encased units of today. They were simple paper tape recorders mounted in the tail section of aircraft with minimal protection. The 1965 crash of an Air India flight over the Swiss Alps demonstrated the fatal flaw of this approach. The paper tapes were destroyed by impact forces that the recorder case could not withstand, and investigators were left with no usable data. That crash, along with several others in the mid-1960s, triggered a fundamental redesign of flight recorder protection. Engineers realized that the recording medium itself needed to be housed in a separate, armored container that could be detached from the main recorder chassis. This insight led directly to the modern crash survivable memory unit, a self-contained data storage capsule that is physically separate from the recorder chassis and mounted directly to the aircraft structure at the tail of the aircraft, the area statistically most likely to survive a crash. The tail-mounted location is not an accident. Statistical analysis of thousands of crashes showed that the tail section tends to experience lower impact forces and is less likely to be consumed by post-crash fires. Every design decision in the modern flight recorder is the direct result of a specific past failure. The titanium case exists because paper tapes were destroyed by impact. The ceramic insulation exists because earlier recorders melted in post-crash fires. The 3400G standard exists because investigators calculated the actual forces experienced by surviving recorders in previous crashes and raised the bar accordingly. By the mid-1970s, the standard had become global. Every commercial aircraft above a certain weight must carry both a cockpit voice recorder and a flight data recorder, each with independent crash survivable memory units. The system is redundant by design. If one recorder is destroyed, the other may still contain critical data. If both recorders survive, investigators can cross-reference the audio and data streams to reconstruct the flight with extraordinary precision. Every decision on this aircraft is a scar from a past disaster. The titanium, the ceramic, the 3400G standard, all born from specific failures that investigators refuse to let happen in vain. If you want to keep uncovering the hidden engineering that turns catastrophe into design, subscribe and stay with this series. The next reveal will change how you hear every click and hum on your next flight. In the comments, drop the word redundant if you appreciate that two independent recorders mounted at the tail exist solely to speak the truth when everything else goes silent. Now comes the convergence that changes your understanding entirely. The memory module inside the modern flight recorder is not a single massive chip etched onto a circuit board. It is a stack of smaller memory chips mounted on separate boards, each board connected to the central processor through a flexible cable. This arrangement serves a dual purpose. It allows the individual boards to shift and move slightly during impact, absorbing energy through relative motion, and it ensures that if one board is damaged, the others may remain intact. The technology is essentially the same as the stack architecture used in solid-state drives, but hardened by several orders of magnitude. The memory chips themselves are coated in a thin layer of protective epoxy that further resists shock and heat. When you put all these layers together, the picture becomes clear. The flight recorder does not survive by being indestructible. It survives by being engineered to sacrifice everything except the data. The outer case may be dented and scarred. The thermal insulation may be charred and cracked. The internal mounting plates may be bent and compressed, but the memory chips must remain intact and readable. This is what the Skybrary documentation means when it says the recorder is designed to ensure that data, rather than the recorder itself, survives an accident. Let that sink in for a moment. The entire engineering project is oriented around a single goal: preserve the information at all costs, even if the physical container that holds that information is destroyed in the process. The recorder is not designed to be reused after a crash. It is designed to be recovered, read, and then retired as evidence. The data lives on a removable memory module that can be extracted from its protective housing and plugged into a specialized reader. That reader must work after the recorder has been subjected to 3,400 Gs of impact, 1,100 degrees of heat for an hour, 30 days of saltwater immersion at 6,000 meters depth, and a static crush force of 22 kilonewtons applied continuously for 5 minutes. The numbers themselves sound like science fiction. They are not. They are the minimum performance requirements written into international aviation law. Every time you see a news report showing a recovered black box being removed from its protective housing and carried to a laboratory, you are watching the result of design decisions made decades ago, tested against actual crashes, and refined with each new failure. The data inside that box is the closest thing aviation has to a time machine. It captures the exact moment when a routine flight became an emergency, the precise sequence of control inputs, the final words spoken in the cockpit, the mechanical signatures of systems failing in real time. Without that data, investigators are forced to rely on wreckage analysis alone, a method that often cannot distinguish between a mechanical failure and a pilot error. With the data, they can reconstruct the flight second by second with the kind of precision that would make a historian weep. Now think about the aircraft you will board next time you fly. There are 2 orange boxes mounted in the tail section, each with its own independent crash survivable memory unit, each containing a separate data stream, each designed to survive impacts that the human body cannot endure for 1,000th of a second. You are not just flying with a backup system. You are flying with a time capsule that will testify about your last moments if everything goes wrong. A silent witness that engineers have spent decades perfecting to ensure the truth is never buried. The next time you hear news of a recovered flight recorder being brought to a laboratory, you will understand what it took for that small orange box to survive. You will understand the layers of titanium, ceramic, flexible cables, and stacked memory boards that allowed a fragile silicon chip to endure forces that destroy steel. You will understand why the recorder color is orange, not black, and why the name black box is a relic of a time when the inner workings of technology were considered mysterious secrets known only to engineers. But the most fascinating part of this story is what happens to the data once it is extracted. The cockpit voice recorder tapes are not simply played back. They are analyzed by forensic audio specialists who enhance the signal, filter out background noise, and reconstruct the conversation with machine precision. The flight data recorder parameters are not simply read off a chart. They are processed through algorithms that reconstruct the aircraft trajectory, control surface positions, and system states in 3-dimensional space, creating a virtual replay of the flight. This virtual replay is then compared against the wreckage analysis to confirm or challenge the physical evidence. If the data says the left aileron deflected downward 2 seconds before the right aileron, the investigators can inspect the wreckage of the left wing to confirm that the mechanical linkage was intact at the moment of impact. The convergence of data and physical evidence is where aviation safety improvements are born. Every design change to modern aircraft, from reinforced cargo doors to improved fire extinguishing systems, can trace its lineage to a specific recording made by a flight recorder that survived a specific crash. You are sitting in a safer aircraft today because a small orange box survived a crash 20 years ago and revealed a flaw that nobody knew existed. That is the hidden economy of aviation safety, a debt that every passenger unknowingly owes to the engineers who designed the crash survivable memory unit. The next time you walk past the tail section of an airliner on your way to the gate, Take a moment to look for the small rectangular protrusion near the base of the fin. That is where the recorder lives. That is where the titanium case sits, waiting for a moment that will hopefully never come. That is where the memory chips sleep, ready to testify. And now you know that the device is not a black box in the sense you always thought. It is an orange beacon of truth, designed to survive the impossible so that the story of what happened is never lost to silence. The next flight you take, you will board with a different kind of knowledge. You will know that the system beneath your feet is smarter than the scenario it was built to defeat. The question that remains open, the thread that loops back to the beginning, is this: what happens when the area statistically most likely to survive a crash is compromised by a design change that moves the recorder to a different location? That question is not hypothetical. It is being debated in engineering conferences right now. And the answer could change everything about how flight recorders are required to be installed. But that is a story for another flight. For now, the next time you see the tail of an aircraft, you will understand exactly what that orange box represents. You will understand what it takes for a memory chip to survive the fall. You will understand what it takes for a memory chip to survive the fall. And here is what that understanding does to you as a passenger. The next time you hear a news report about a retrieved flight recorder, you will not just hear about a piece of equipment recovered from a debris field. You will hear the story of a titanium shell that withstood forces that should have vaporized it, a ceramic heat shield that kept silicon chips cool while the world around them turned to ash, and a stack of mounted boards that bent and flexed to preserve the single most valuable piece of evidence an investigator can ever hold. So the next time you hear about a recovered flight recorder, you will not just hear about a piece of equipment. You will hear about a design philosophy that valued information above all else. If that shift in perception resonated with you, subscribe to AV2 so you never miss the hidden stories written into every rivet and circuit on the aircraft you board. And in the comments, drop one word: irreplaceable. Because now you know exactly what that word means when it comes to the truth that survives the fall. You will hear the story of a design philosophy that treats information as the only truly irreplaceable cargo on any aircraft, more precious than the passengers, more valuable than the engines, more critical than the fuel. The flight recorder is not built to survive. It is built to ensure that if the aircraft cannot survive, the truth of its final moments will. That philosophy extends far beyond the recorder itself. Every system on a modern airliner is designed with the same layered defense architecture, the same assumption that failure is inevitable, and that the only meaningful response is to engineer for the failure scenario with the same rigor as the normal scenario. The hydraulic system has multiple independent circuits. The electrical system has multiple independent generators and batteries. The flight control system has multiple independent computers running multiple independent software versions designed by multiple independent engineering teams. Each layer is a confession that no single system can be trusted. Each backup is an admission that the primary system will eventually fail. Each redundancy is a promise that the failure of one component will not mean the failure of the entire mission. The flight recorder is the ultimate expression of this philosophy. It is the only system on the aircraft that is not designed to help the aircraft survive. It is designed to survive the aircraft. It is the witness that will testify when the defendant is no longer able to speak. And now you understand why that small orange box at the base of the tail is not just a piece of technology. It is a monument to the humility that defines aviation engineering. It is the admission that every system ever built will eventually fail, that every pilot ever trained will eventually make a mistake, that every flight ever taken will eventually come to an end. The box does not prevent those failures. It does not offer any protection to the passengers. It does not give the crew any additional capability. It simply waits, in silence, for the moment when its function becomes essential. And when that moment comes, it performs its function with a reliability that exceeds almost any other system on the aircraft. The recorder will be there. It will do its job. It will survive. That is not a guarantee of safety. It is a guarantee of accountability. It is an assurance that if something goes wrong, the truth will not be lost. The data will be recovered. The story will be told. The lessons will be learned. And that quiet promise, embedded in a titanium case wrapped in ceramic insulation and mounted to the tail of every aircraft you will ever board, is perhaps the most profound statement that engineering can make. It says that the designers of these systems trusted the process more than they trusted themselves. They knew that perfection was impossible, so they built a fallback that would preserve the memory of imperfection for those who came after. Every time you walk past the tail of an aircraft, you are walking past a silent testament to that trust. The orange box does not need to speak. Its presence is enough. It says that the people who built that aircraft understood that failure is part of the design, that the only true failure is the one from which nothing is learned. And that is why the flight recorder is not just a black box. It is a philosophy in metal and silicon. It is a promise that the truth will outlive the crash. It is a guarantee that the next flight will be safer than the last, because this box was there to catch what the previous one could not hold. You board your next flight with that knowledge. You settle into your seat. You hear the familiar thump of the cargo door locking. You watch the wing flex as the engines spool up. And somewhere behind you, near the base of the tail, two small orange boxes sit in patient silence, ready to do the one thing they were built to do. And you understand exactly what that means.